we've used direct substitution for finding limits a couple times before. It's really a matter of seeing when we can, though. And so you notice specifically here it tells us that we can use direct substitution with polynomial functions, rational functions, and we can use it also for roots. But notice we just can't use it on a root at the endpoint to find the limit. Because remember, if we're looking at a root, at least for an even root, our graph might be looking something like this. If we're looking for the limit at that endpoint, there's a limit from the positive direction, but not a limit from the negative direction. Hence why the limit wouldn't exist at the endpoint. But every other point that's actually in the domain, you can do it. But notice that phrasing there. For values in the domain. They all have to be values that already exist. So like I didn't have to specify for a square root anything over here. We can't use those because that's not part of the domain of that particular function. All right, so let's go ahead and see how that would work. Nice and simple. There you got an example of it. The limit is x approaches 3 of 2x squared plus 3x plus 5. We can just use direct substitution to find out what that is. In other words, for direct substitution, you're just going to take whatever x is approaching and you're plugging that in for x wherever x appears in the equation. All you got to do for finding limits like this. These are the easy ones. These are the pretty ones. And so we start with those. So we're just going to be doing 2 times 3 squared plus 3 times 3 plus 5. And that's all you got to do. So figure out what that's going to be. So that's going to be 2 times 9, which is 18, plus 9, which is 27, plus 5. Final answer is 32. So as x is approaching 3 here, our function value is approaching 32. So that's like saying that the y value is approaching 32. Depending on your purpose and what you're doing with a particular problem, you could say it either way. Function's approaching or y is approaching 32. And so for each of these cases, because the first one was rational and we weren't at an asymptote or anything, and the second one was a root and we weren't at the end point, all we could do is just plug in the numbers, see what they equaled, and yeah, those are our limits. That's what each one's approaching there. And so you've added all of these limit laws into your notes, but then some details about these. A lot of these might seem fairly self-explanatory. You know, well, if you're trying to find the limit of two functions that are added together, you can find the limit of the first function plus the limit of the second function. It seems kind of intuitive that we'd be able to do that, but when we actually start looking at equations, it isn't always as intuitive, especially when we start taking a look at information from graphs, as we'll be doing to start with. And so some of this information will first seem obvious, and then it's going to seem less obvious. So expect that to happen. The one thing that, though, is a little less obvious, but is actually going to have some cool implications for future work we do in here, is that third one, where we have the c times f of x. Notice what happens in that limit. C is just a constant there, of course, and when we find that limit of c times a function, it equals the same thing as the limit of the function itself, and you can find the limit first and then multiply by c. And so it's saying that we can actually pull that value out. And actually that's because of a rule that we're going to be adding into this here in just a moment as well, because there's more notes to get down. And as you take a look at these notes, you'll notice all of this stuff up here is the same. So it's just all of this still meets the same requirements, but this is the stuff that's new. This is the stuff that you haven't written down yet, that you're just adding to the list. All right, so looking through these, some of these are a little less obvious. Now, certainly those first two, the division and the exponent, if you're just guessing what would happen, that's probably what you would end up thinking. But notice those second two, the last two. the limit as x approaches a, so that is the limit as x is approaching anything, it doesn't matter what x is approaching, of c, that is a constant. So if we're looking at the limit of a number, the limit on that will always equal the number. And then finally, the limit as x approaches a of x will always equal a. Now, if you think about the graphs of what those would look like, that can actually help with these. So let's take a quick look here at what that would mean for us. So like, if we were graphing the limit as x approaches a of c, so if we graph just y equals c, let's make up a number. Let's say it's y equals 5.
Oh.
The graph of y equals 5 is a horizontal line. That's up at 5. Right? Well, we want to know as x is approaching some value. So like let's say that x is approaching
3.
1 here. What's our y value? 5.
5.
If x is approaching 3, what's the y approaching? 5.
5.
And so when we think about this back to the graph, we can see that because it's just a horizontal line, that's why the limit of c is going to just be c. Actually, let's just erase that instead of scribbling it out. All right, and then for the second one, we can think about it the same kind of way. The limit as x approaches a of x. Well, in this case, we're looking at what would the graph look like if we were going to be graphing y equals x. Well, that, of course, would be a line with a slope of 1. And this line, of course, it's going through the origin. And so at any given value here, let's say if x is 3, your y value is 3. If x is approaching 4, y is approaching 4. Hence y, no matter what x is approaching, our limit is going to equal that value of what we're approaching. But again, it's because I can visualize the graph in order to know that too. Which is also nice because if we forget some of these, it gives us an in to be able to find them again. So as you take a look at these last two rules that you put into your notes here, you actually only have one rule here. Technically speaking, this second one that's dealing with roots is the exact same thing as the first one. It's just dealing with what the case would be if it was a fractional exponent. And so the fact that we have all this stuff about positive integers means we make it two separate rules, but it's really the same idea, right? Because roots and exponents are the same thing. Now, why do we have that positive integer stuff? Well, imagine if it was a negative exponent. Well, then all of a sudden we're looking at like 1 over a value. And so then it's changing what's happening in terms of the limits and all that stuff because there's some division involved and some subtleties can become a part of it. So for now, we're just worrying about these for positive integers and calling that good. Now, I want to go ahead and use these concepts a little bit. We're going to practice using these rules with this setup. So you got the graph, you got f, you got g, and we're going to be able to figure out all of those different problems. Start by making a copy of the graph on your paper, and then we'll go through together how to find these limits and how we can use those rules to do that. All right, so taking a look at this first limit that we need to find here, if we're going to figure out this whole limit, we're going to have to use our limit rules. So first up, remember that the addition inside, I can break that up into two separate limits. So I can make this into the limit as x is approaching -2 of just f of x plus, then we do the limit as x approaches -2 of 5 times g of x. Okay, but now, again, I don't necessarily know what that part is going to give me. So I need to take one more step to simplify that a little bit. So the first part, the limit as x approaches -2, that's going to be unchanged here, of f of x, plus, now I've got a constant multiplied inside. The number 5 just multiplied inside. Remember that the limit as we approach a constant is itself. That's why we have the rule that the constant can be pulled out, and I can just turn it into 5 times the limit as x approaches -2 of g of x. Now that I've written it that way, I now can actually figure out what that whole thing is going to equal. So the limit as x is approaching -2 of f of x. So I go to f of x, the purple graph up here, and I want to see what's happening, what the limit is as x approaches -2. So -2 is over here. Go to f. What is the limit? It is 1, yes. I don't want this number. That is f of -2, not the limit as x is approaching -2. It's different, remember. So from the left it's approaching 1, from the right it's approaching 1. That's why, yes, it is just 1. So it's going to be 1 plus 5 times, okay, now I need the limit as x approaches -2 on g. Okay, so go over to -2, go down to the g graph. What is it approaching? -1 in this case. And so it's going to be 5 times a -1. All right, so now I can actually find the answer finally. So 5 times -1, of course, is -5, plus the 1 gives me -4 as our final answer there. All right, so for the second one then, the limit as x approaches 1 of f of x times g of x. I don't want to start by doing f of x times g of x or something there, because I can't see that graph, what f times g of x would actually look like. So instead I break it up into 2 separate limits. The limit as x approaches 1 of f of x. Okay, what is the limit as x approaches 1 of f of x? That's going to be 2. And I'm going to multiply that by the limit as x approaches 1 of g of x, which is?
D and E?
Yeah, now we got a problem here, because notice from the right, that is from the positive direction, it's -1. From the left, it's going to be -2. And therefore, it does not exist. So, since I can't do 2 times undefined, it's just going to be does not exist. I'll call it DNE. You can write undefined as you wish there.
What about 2 D and E?
All right.
2 times.
Next up, limit as x approaches -1. So I'm looking along this line here. And I want to figure out what f of x divided by g of x is going to be. Well, that's going to be the limit as x approaches -1 of f of x. That's this value. You notice we got to do a little estimating there. And yes, you might end up with a different answer than I do here, but I'm going to just call that 0.5. And then we need to know what g of x is, what it's approaching as x is approaching -1. Well, that's going to be this value down here. Again, different estimates can work, but I'm going to go ahead and call this 0.25, but that's 0.25 down, so that should actually be a -1.25. All right, so then it's just a matter of do that division. And so we do that calculation, we end up getting an answer here of, I believe it is -0.4. All right, good. Next one, we're looking for the limit as x is approaching -2 of x squared times f of x. Now there's an x squared in there. Well, remember, that's going to be the same as the limit as x approaches -2 of the x squared. There's a different color there. And the limit as x approaches -2 of the f of x. And I can multiply those. Now, how would I find the limit as x approaches -2 of x squared?
Well, it gives you.
Well, remember how we started today? We can find a limit by direct substitution.
Yeah, you just substitute.
I can just put that -2 in for x there. So what is -2 squared? 4. Okay, so the limit as x approaches -2 of x squared is 4 then. And I'm going to multiply that now by the limit as x approaches -2 of f of x. And so I'm going to go over here to -2. What is f of x approaching? 1. And so it's going to be 4 times 1, which equals then, of course, 4. All right. Last one now. All right, so for our last one, remember that if I'm finding the limit of a square root, I can get the same thing by doing the square root of the limit. And so I'm going to end up doing the square root of the limit as x approaches 2 of 5 minus g of x. Well, what's the limit as x approaches 2 of 5?
5.
It is 5. Because this is a constant. The limit of a constant is just going to be itself. So that's going to be 5. Minus, now the limit as x approaches 2 of g of x. Okay, so go over to g of x, and where x is 2, g of x, yep, it looks like it's hitting 0 there. It's approaching 0 from both sides as well. Okay, so it's going to be 5 minus 0. So we're doing the square root of 5 then. And so really then that's going to be your answer. Your answer will then just be the square root of 5.